I'm Emily.
And I'm IBK. Today we'll be showing you how to solve an RL and RC circuit in the Laplace domain.
Inductors resist instantaneous changes in current by storing it. It can supply current to a circuit until it has been discharged.
Capacitors prevents instantaneous change in voltage. It stores energy due to the presence of the charge difference that arises from the accumulation of positive and negative charges on the capacitor plates. This stored energy powers the circuit even after the source is cut off. In the time domain, resistors, capacitors, and inductors are represented as R, C, and L.
In the Laplace domain, resistors are R, capacitors are 1 over Cs, and inductors are SL. Solving an RL circuit.
Let's take a look at this simple RL circuit. First, we're going to convert from the time domain into Laplace domain by changing R and L into their impedance forms. For R, this is simply R, and for L, it's just SL. We're going to represent this by drawing a box. R1 stays R and L1 becomes SL. So here we have our circuit redrawn with the components in their corresponding impedance forms. And now we're tasked with finding the transfer function h of s, which we know is just V out over V in, and in this case V in is V source. So we can simply treat this as a voltage divider. And this means that we need to solve for the impedance over VO, which we know is simply R1 and L1 in series, over the total impedance, which is RL, R1, and L1 in series. So we can write this as VO is equal to VS multiplied by R1 plus SL1 over R plus SL plus R1 plus SL1. And this we recognize is just our transfer function, because remember, transfer function was equal to V out over Vs. So if we divide V out by Vs, we're left with this as our transfer function. So finally, we can write this as h of s is equal to R1 plus SL1 over R plus SL plus R1 plus SL1. And this transfer function has several useful applications.
Now that we have an understanding of how to solve an RL circuit, let's take a look at an RC circuit.
So this is an example of a simple RC circuit, and I've gone ahead to convert the circuit from the time domain to the Laplace domain. So the first impedance is just simply representing the R1, and the second impedance for the capacitor is representing 1 over SC2, and this is just representing 1 over SC1, and the last impedance there is just representing R2. Okay, so we are going to go ahead and solve this circuit. So we're going to simplify the circuit first by finding a voltage right here. So that way we'll use a voltage divider to find the voltage right here and use another voltage divider to find the voltage right here. So in order to do that, we are going to combine these three impedances into ZEQ. And I'm going to redraw that so that way you guys can see it clearly. So we'll have our V source with impedance 1 with our ZEQ, and we can just say this is VZEQ. And from here, we can go ahead and just simplify what ZEQ would be. So to find ZEQ, we can see that these two impedances are in series, and both of those are in parallel with this impedance right here. So we have ZC2 plus ZR2, all of those in parallel with ZC1 equals our ZEQ. From here, we can go ahead and simplify this further. We have Z2 plus ZR2 plus, well, multiplied in this case with ZC1 over ZC2 plus ZR2 plus ZC1. All of these equal our Z equivalent. So now we can go ahead and solve for VZEQ. So VZEQ would be just basically a voltage divider across this equivalent impedance. So we'll have VS multiplied by ZEQ over ZEQ plus ZR1. So now we can redraw the circuit with knowing our VZEQ. So our VZEQ is the voltage going across this capacitor, and that is already included in the calculation for our VZEQ, so we don't have to include the capacitor here. And we still have our ZC2 and ZR2 and V0. And so from here we can go ahead and solve for our V0. And again, doing a simple voltage divider, we have V0 equals VZEQ, which is our new VS in this case, multiplied by ZR2 over ZR2 plus ZC2. Now that we have each component, we can go ahead and just plug in our VZEQ right there, and then we can go ahead and find the transfer function. So we have V0 equals VZEQ, so VS ZEQ over ZEQ plus ZR1 multiplied by ZR2 over ZR2 plus ZC2. And from here, we can find our transfer function, which is just V0 over Vs, which is ZEQ over ZEQ plus ZR1 multiplied by ZR2 over ZR2 plus ZC2. This is our transfer function, H of S. Okay, so I went ahead and plugged in the Laplace transformation to get this final transfer function right here. It is a bit of a work to get from solving that to the final step, but I know you guys can do it. So basically with this transfer function, we can plot the magnitude of a body plot. We can also draw a phase diagram for a body plot.
We hope this helped you guys understand how to approach solving RL and RC circuits.
Thanks for watching, guys.
Bye!